Okay, so long we have discussed just one random variable and function of one random variable. Okay, we so far did not discuss what is called joint variation. That is, earlier we considered a random variable x, its probability density, probability distribution, and a function of this random variable and all that. Similarly, there could be a separate random variable y. We discussed its properties and all that. But there is an important topic actually where x and y, they are two random variables which are mutually related. That is, the underlying process is such that x and y has got some kind of interconnection, I mean interdependence rather. Okay. Then the question of not individual variation, but rather joint variation and joint statistics comes. For instance, you can consider these two variables. One is say temperature of the environment, okay, and humidity in the environment. Now, temperature could be a variable T, humidity could be H. Now, you all can visualize that the underlying physical process is such that definitely one depends on the other. Surely, if the temperature is high, there will be some kind of humidity, one type of humidity. If the temperature is less, another type of humidity, and vice versa. Okay. Now, we do not go into this physical modeling because that is very difficult, but we treat both T and H as two separate random variables which are jointly related, mutually related. Okay. Obviously, I mean, because if T is high, maybe H will be less or H will be high. Again, if H is less, T could be high, less, because that is determined by their mutual interdependence. Okay. So, we define. So, our topic today is in fact, now we are considering two random variables, but in general it will be say n number of random variables. Okay. So, we will extend this concept to more than two number of random variables. So, we now consider always a pair under this topic, always a pair. X is a random variable, y is a random variable, but since they are related, we consider x, y. Okay. In that case, we have to define the joint probability distribution of x and y. Now, what does it mean? Let us give a definition actually. We consider the event. This random variable x taking value less than equal to some given number capital X, y taking value less than equal to some given number capital Y, okay, which actually means this pair is taking value from a particular region D in the xy plane. What is that region? Suppose this is the xy plane, xy, and this point is your capital X, capital Y. Then if you draw this line, this area is D. Okay. Obviously, within this area, both these are jointly satisfied. Both x less than equal to y, x, capital X, y less than equal to capital Y. See, if x and y, they are not considered together, then we consider only x individually. In that case, the probability distribution of x was what? We would have simply taken this vertical line and the entire plane to the left corresponds to points where x is less than equal to capital X, independent of whether y is less than equal to capital Y or higher. But since we are considering the joint variation, okay, that is under tighter condition, that not only x is less than equal to capital X or y less than equal to capital Y, but they are being satisfied simultaneously. This is the simultaneous variation or joint variation. Okay. So, probability distribution will be actually the probability of this event, that is is nothing but the probability of the event that I have shown, that is the pair x comma y falling within this zone. Okay. There is a probability of this event. Okay. Now, some of the definitions, some properties follow immediately from this. What are the properties? First, this is equal to 0. Okay. Why? It is very simple actually. What is f x minus infinity? It is actually the probability of this event. So, if I am writing like this, actually I should write in a different way. I mean, I should say that it is x, y, excuse me, the probability that x less than equal to capital X and y, there is nothing called less than equal to minus infinity. So, but this is the event, this event is basically a subset of this event. But probability of this event, as we know from our earlier definition, is 0, okay, which means this probability is 0. So, this is equal to 0. By the same way, we can have equal to 0. For that, this should be equal to 1 obviously, because this covers that entire plane. All points on the xy plane are covered by this. The event, that is the event, actually consists of all pairs or all points of the xy plane, and obviously the corresponding probability distribution will be 1, because it considers the total set. Okay. Then consider this. What is the probability of x taking value less than equal to some capital X2 greater than x1 and y taking value less than equal to some y? Okay. This means we can always write it like this. See, the event consists of this thing, x should be lying within this zone less than equal to capital X2 but greater than x1, and y less than equal to capital Y. Now, this is the event. Now, this set can be written as a combination of two non-overlapping sets, non-intersecting sets. One is this event actually. Okay, let me make one small correction. We know that okay. So, instead of capital X, if we put x2, small x2 you can say. Okay. Now, this set or this event can be written as a union of two non-intersecting sets, two non-overlapping events. One is this, another is so y remains less than equal to y, but this zone is separated into two zones. One is for x lying as less than equal to x2 but greater than x1. In another case, x is less than equal to x1. Now, this is what I wanted. And what is this? This is simply f x y x 1 y, which means this probability is nothing but, this is nothing but f x 2 minus, sorry, in fact I can erase these. In the 2D plane, it means what? But suppose x 2 is here, x 1 here, okay, and this is y. That means this is the area of interest, where x is less than or equal to x 2 and goes up to x 1, but does not touch x 1, which is greater than x 1. So, this was the event. Okay. This probability is nothing but the pair x comma y taking values from within this, I mean is falling within this zone. What is the total probability of that? That turns out to be this. On the other hand, by the same logic we can say okay, just give me a minute please. By the same logic, we can say that x is probability y lie within two zones, within two limits y1 and x less than or equal to some capital X. Okay. I do not think I have to repeat anything. You can just apply the same logic and get this. This will be what? y2, this is larger one minus y1. In the 2D plane, xy plane, it means what? But suppose this is x, okay, and there are two values. This value is y2, this value is y1. Then this is the region. What is the probability of the pair xy falling within this region? Okay, that is given by this. This now we can generalize further. Okay. How about a more general thing, that is probability of x lying within two limits and y also lying within two limits. What is this? Now, you can easily see this. If I draw the 2D plane, this means that if this is y2, this is y1, if this is x1, if this is x2, then this is the region, right? This probability means what is the probability of xy pair taking values from within this region, I mean falling within this region, or xy pair taking values within this region. What is it? Now, you can see one thing. If I do not limit myself to this box only, but go down fully, then what I get is nothing but what I already obtained. That is, if I am interested in this, that it remains as it is, but y is only less than or equal to y2. So, I go down fully. This event I have already known its probability, it was calculated in the previous page, but this event is nothing but, this set is nothing but the union of two non-intersecting sets. One is the what? One is this box, another is the box below. That is but in another case y2 greater than y1 and p first component remains as it is and y less than equal to y1, obviously. Okay. Now, this is my quantity of interest. I wanted to find out what it is. I know what it is. I know what it is. It was derived earlier. This is what? F of x2 comma y2 minus f of x1 comma y2. And this is what? F of x2 comma y1 minus f of x1 comma y1. Okay. So, in fact, I can write down first component is what? F of x2 y2, that is this point, minus f of the other component is, here f of x2 y2 minus f of x1 y2. What is x1 y2? This point. Okay, and take this quantity to the left, so sign gets reversed. Originally this was f of x2 comma y1, now that becomes that comes with a minus sign, and the other quantity which was present with a negative sign. What is that quantity? F of x1 comma y1, that comes with a positive sign. So, this is equal to what we wanted, this quantity. Less than okay. Remember this. I will need this expression later. Okay. So, from probability distribution, next thing that comes is probability density as before. You remember what I did last time in the case of single variable? We had f of x as the probability distribution function of a single random variable. Then the derivative of that was what? That was the probability density. Like that is, if f of x denotes the probability distribution function, then del f del x was p of x, which is the probability density. What is the physical meaning of it? That if at any point x and between a, if I consider a point x, then what is the total probability of x falling between x to x plus dx? That was px into dx. All that was fine for the one dimensional or one variable case. We will just generalize that concept or that notion to the two variable case. So, here we define the joint probability density function. Since we have got now two variables, these are all partial derivatives. Sorry. Remember, this is partial derivative, and sometimes I do not write in the general form where f, then you have a subscript x y, then the values of x y. When I just write f as a function of x and y, I just put as unknowns, no known quantity given. There is a general form of the function. I simply put x variable and y variable here. Okay. This is the probability density. Why it is probability density? Okay. Reason is, if I consider any region say D in the xy plane. Okay. Then what is the probability of xy falling within this region? We will show that that will be nothing but this integral over this zone. I put double integral because dx dy over this zone. Okay. And what is px comma y dx dy? Okay, let us see what it is. Consider this point x plus delta x, y plus delta y, and this is x, y. Of course, in the figure it appears to be a very big area, but this is actually infinitesimally small area because this is delta x, delta y. Okay. Just for our convenience, I have drawn a reasonably big sized area, but actually the area is very small, infinitesimally small, because delta x and delta y are small and they will be in fact tending to 0. Anyway, what is the probability of x comma y falling within this zone? We have already seen that probability, that is, what is the probability of x lying within x plus dx and y not that we have already seen from the previous example, that was equal to what? Minus sorry this point. So, then this point okay. This is the probability, and if I divide this total probability of x y falling within this zone by delta x times delta y, and let delta x approach 0, delta y approach 0, then what we get is nothing but the probability density. That is the meaning of this partial derivative actually. That is, when I say the del square f del x del y, it means find out in a rectangular area of sides delta x and delta y located at point x y. Okay, what is the probability? What is okay? What is this differential? Okay, that divided by delta x delta y. That is, what is the probability of x y falling within this zone? That is this divided by delta x delta y, and let delta x tend to 0, delta y tend to 0. That will be equal to probability density. That is, I can erase this. That is Okay. That means, if I now take a very small, infinitely very small rectangular area, where the rectangle has rectangular area delta x delta y, meaning the sides are delta x and delta y, then what is the probability of x y falling in that area? That is simply p x comma y times delta x delta y. Okay. I repeat again, what is the probability of x y pair falling within that infinitely small rectangular area delta x delta y located at the point x y? What is the probability? Obviously, that will be equal to p of x comma y times delta x delta y. So, what is the probability of x y pair falling within the total region D? It will be nothing but a summation of this infinitesimally small probabilities over the entire region. That is, I can break up the entire region as a union of such infinitesimally small rectangular areas. So, total probability will be nothing but a summation of these individual probabilities, and it is a continuous summation. So, we get that integral relation, that is p of x y dx dy integrate over this entire region D, that will give you this thing. Okay. There is a probability of x y falling within this specified region D. Okay. Next, we move to another definition, which is called marginal statistics. Suppose it is given that two variables x and y, they are jointly random variables. So, we are giving the joint statistics like joint probability density, joint probability distribution and all that. In this scenario, when I consider just one random variable separately and take its individual statistics like its own probability density function, probability distribution function and things like that, then that will be called the marginal statistics of the random variable x. Okay. You can easily see that if I say this means as usual the probability distribution of x, that is small x taking values less than or equal to capital X, where capital X is a specified number. This is the probability distribution. This will be called the marginal distribution of x, where x, y are jointly random. Now, this is nothing but why? Sorry, it will be plus infinity, not minus. Minus b will make it 0. We have seen already. Okay. Obviously, it will be that in the 2D plane. As such, suppose we take at point x. Okay. We come back to this previous figure. Suppose this was capital Y, this is x y of course, and this region we are considering this region earlier. That was the total probability of x y falling within this region was f x y capital X comma capital Y. But if this capital Y moves to infinity, then this will be nothing but the probability of just x taking value to the left of this line, that is x taking values less than or equal to capital X irrespective of whatever y, okay, or all possible y's were considered. So, in fact, that region will give you all possible all possibilities by which small x can take values less than or equal to capital X. Okay. So, obviously, when it is infinity, that is when this line goes up to infinity, that is I have the total plane to the left of capital X line, x equal to capital X line. That half plane indicates what? That half plane altogether considers all cases where small x takes values less than or equal to capital X. Okay. Now, there is no condition on y, because y equal to infinity means all y's are covered, all y's are possible. So, I am left with x only. So, I get these. Okay. So, by the same token, I will not repeat it. This will be nothing but okay. And finally, this is very important. P, I write formally here P x capital X, that will be nothing but by the way, I forgot to mention one thing. So, it is very clear, we should always at least write it out. We have seen that del square f del x del y, okay. This was P x y, which means where x and y are any general variables now. So, that is why I am not putting them in the subscript and putting some specified values here. This will be nothing but double integral of, you can put limits x and minus infinity. This comes from ordinary calculus, so I cannot go back to that. P x y dx dy. So, this derivative, so this is an integral relation, reverse. Okay. So, now I come to what I was doing. This will be P x y or let me write it in a more simplified way. This was becoming complicated. Just P x, I am putting a general variable x. This is nothing but so integrate it out with respect to y, it becomes a function of only x, and that will be P x. Okay. When I write P here and this P, these two are defined functions. In fact, that is why I should have put P subscript x and this is subscript x y. These two are two defined functions. This is a probability density function of x, this is a joint probability density function of x and y. Though I use the same symbol P, these are actually two defined functions. And similarly, okay. It is not very difficult to show that. After all, we have seen that we have just a while back seen we put some excuse me. Actually, to be very correct mathematically, I should not use the same symbol x y here, because they are coming in the limits. Sorry. So, let me put alpha beta. Okay, that way it is better. So, obviously, if I differentiate it with respect to x, this goes, I am left with only this. Okay. And what is this f? F was x y. Now, if I put y equal to infinity, then in this integral this will become infinity, of course, and here okay. But we have seen what is f x comma infinity, that is nothing but f x, and what is del f x del x, which is in fact df dx now, because it is a variable, it is function of just one variable. So, del f del x actually means df dx, that is nothing but the probability density of x. That gives the proof, that is that gives the proof, that is your P x is nothing but, you can put down x y here also, does not matter. Okay. The other one also follows very easily. Okay. Now, we take an example. Earlier, we have seen that x is a random variable and x was taking values like x was following some distribution of density like normal, that is Gaussian or uniform, okay, or maybe we took binomial or Rayleigh or things like that, Poisson, of course. Okay. That time x was only individual random variable, single random variable. Now, we consider similar example for joint random variables, like what is meant by two variables which are jointly Gaussian. Now, two variables are jointly Gaussian if their probability density follows this function. Some a times exponential okay, just a minute. Times within bracket where you see this has to qualify for a probability density function. So, it should always be non-negative and its integral over the entire plane xy plane, sorry, this will be y. No, this I made a mistake, sorry. This is a very special case, so this is a mistake, let me correct it first. So, this is a very big expression actually. Okay. So, this is a function of two variables x and y. So, in order to qualify for in order to be qualified as a probability density function, this should be non-negative everywhere and its total integral over the entire xy plane should be equal to 1. That will be satisfied provided A should be equal to r square and r should be such a quantity whose mod value is less than 1. So, A should be such, A should be this and mod value of r should be less than 1. In that case, if you integrate it over this entire xy plane, this will be equal to 1 and this will always be non-negative. Okay. So, this is just a condition. This will be jointly Gaussian. In fact, what is mu1, what is mu2 you can now see. We can find out the marginal statistics of x and y. We will see that x and y, they are individually also Gaussian random variables and mu1 is the mean of x and sigma 1 is the sigma 1 square is the variance of x. Similarly, mu2 is the mean of y, sigma 2 square is the variance of y. Okay, that is the marginal statistics we can obtain from this. But this is the formula for, this is the expression for joint Gaussian density, okay, where A is this and R is to satisfy this condition. Actually, the meaning of R will come later. It is the cross correlation or correlation say between x and y. Okay. Now, how do you show this? Okay. How do you show that under such case x and y both are also individually Gaussian random variables with means mu1 and mu2 respectively, variances sigma 1 square and sigma 2 square respectively. Okay. For that, I just consider this quantity. Okay. This quantity can be written as, I mean, very easily in this manner. We can write that quantity simply as minus r times whole square. So, I am bringing an additional term. So, this has to go out 1 minus r square into y minus same thing whole square. Okay. So, suppose I will find out P y. Then it will be nothing but dx. If you integrate, so this part has no x, so it will come out. So, we will be getting a times exponential. This gets some cancellations take place with this and the other term which lies outside, that is 1 by 2 within bracket 1 minus r square. So, 1 minus r square 1 minus r square cancels, you get this thing, there is a minus sign also. So, you get and within the there is an integral exponential. I have no space. So, I just say that this quantity this comes over here, okay, dx. This integral, even though there is a y present, and it is very interesting that this integral does not depend on y, simply because we are integrating with respect to x. Suppose this entire quantity x minus mu 1 by sigma 1 minus r times y minus mu 2 by sigma 2, you call it x prime. Okay, I am just telling you, giving you the hint. In that case, dx by sigma 1 will be dx prime. So, sigma 1 will go out. So, dx will be sigma 1 times dx prime. So, sigma 1 will come out. Okay, and what will be the limits when x is minus infinity, x prime also minus infinity. So, this limit will remain. When x is plus infinity, x prime also is plus infinity, this limit will remain. So, we will have some sigma 1 times exponential some quantity called x prime whole square dx prime, and this integral exponential x prime whole square dx prime. Okay, this is a constant. Okay, if you take that sigma 1 also, sigma 1 or sigma 1 square whatever, along with this you can call this integral to be just a b, which is independent of y. Okay. So, you get a b times this quantity, but this has to be a probability. Okay. And we know this already takes the Gaussian shape, y minus mu 2 square whole square by twice sigma 2 square. So, that means I repeat again, P y then becomes A B okay. And obviously, this is this takes the Gaussian form because of this kernel, and as a result that a b has to be equal to 1. So, that means the integral has to be equal to 1 from the Gaussian kernel. Obviously, a b should be equal to 1 by root 2 pi sigma 2 and this. Okay. So, it is clear that mu 2 is the mean. It is clear that P y, that is the individual, the marginal statistics, marginal probability density of y is Gaussian with mean, that y has a mean mu 2 variance sigma 2 square. By the same token, by the same analysis, you can also prove that marginal density, that is P x, also is Gaussian, and in that case x has a mean mu 1 variance sigma 1 square. Okay. This was for continuous variables. So, we can just repeat these things for discrete variables also. Suppose x and y, they are two discrete variables. X takes values from this set. I mean, why? I mean, it may not be finite. So, let me not put it this way. X I, X j, and like that. It could be a finite set, it could be infinite set. Similarly, y k, y l dot dot like that. Okay. In that case, the joint probability that x takes the value x I, y takes the value y j is denoted by P I j. Obviously, I and j can put double summation, that should be equal to 1, excuse me. okay, and Pi, that is obviously Pi k, and summed over all possible k's, that will be Pi, okay. If Q j is the corresponding probability of y equal to y j, this will be again equal to Pi is the probability of x equal to xi, that is this summation. Pi k is the joint probability, and here it is Qj is nothing but again Pi j, but summed over I. Okay, this is pretty obvious. So, in today's class we conclude here. We will stop here. Okay, we continue to expand on this theme, getting into what is called probability mass. Then a very important concept called statistical independence, then joint characteristic functions and things like that. That will be for the next time. Okay, thank you very much. Okay, so last time we were discussing two random variables, that is the joint statistics, joint probability density, joint probability distribution and things like that. Okay. Then a question that a very important question, a very important point or property is rather the statistical independence of two random variables. That is, when can we say that the two random variables x and y, they are statistically independent. Now, to answer that, let us go back to some of our earlier discussions. Okay. Suppose we have got two probability spaces, one is S1 that has the outcomes say theta 1s, that is set of all outcomes, okay, and A be a particular outcome. Similarly, suppose S2 given, okay, theta 2 and B. Theta 2 is the set of all outcomes here, this is another probability space and B is a particular outcome. Okay. In that case, we have seen one result that the joint probability of this event, or maybe instead of calling A to be an outcome, it will be better or more general if we say A is an event, that is a set of outcomes, and B also is an event. So, let me erase it. Okay. So, what is A B? This is joint event, that is we have got both these experiments going on. Theta 1 was the set of all outcomes, theta 2 is the set of all outcomes, A particular event, B a particular event. A B means joint event, A occurring and B occurring simultaneously. What was this probability of this joint event? That we had seen was given by either like this, P A by B into P B was equal to also P B by A into P A. In case you have forgotten, we can also see how it is comes. That is, suppose N is the total number of trials, out of these total trials, actually we are observing both, I mean outcomes from or events from S1 and S2 simultaneously, parallelly. Okay. Suppose on N A B occasions, event A B occurred, events A B occur, and on N A
on say n b occasions, number of times, this also number of times, number of times the events A B occur, that is A and B occurring simultaneously, that is N A B, and N B is the number of times B occurs. P x z minus y, you can write it as P x minus of y minus z. So, first plot this function P x minus y, you can call it, give it even a name, P say 1 y, you can call it say P 1 y. Okay, you get some function. Okay. Maybe I should not draw the function same shape for both the functions. Maybe suppose it is like this. But you want to evaluate this function at z, so it should be P 1 y, sorry, this is so it will be P 1 y minus z. So, you have to shift it to the right by z if z is positive, or shift it to the left by z if z is negative. So, you shift it by z and then you multiply this function and this function. See the overlapping area, multiply them and integrate. That will give rise to this integral. This is a typical way of, a very standard way rather, of carrying out convolution integral. So, in the next class, we will carry out some example, okay, of this, that is two random variables x and y, okay, and they are having some particular probability densities for each. You form a random variable z as a summation of x and y. Okay. What sort of shape, what sort of probability density function you will have for z? Okay. That we will evaluate by carrying out this convolution integral. Okay. So, that is all for today. We start from here in the next class. Thank you very much.